Okay, so this will be a short video segment. The last one was running quite long. What we're going to do in this video segment is talk very quickly about a couple important definitions related to power and efficiency. Okay. So first of all, let's define power. Power is equal to du dt. This means this is the same u that we use to denote work. So power is how quickly work can be done. Now, that's a really important conceptual point to take away with you. If you think about the difference between, a 100 horsepower car and a 1,000 horsepower car, either car can get you to the top of a mountain. The fact that the 1,000 horsepower car can get you there faster is actually a direct measure of its power. For those of you that are familiar with athletics, you've probably heard people talk about power as explosiveness. Same thing, something about getting a certain amount of work done more quickly. To illustrate this, I'll have a link to a video included just after this video, and I think it'll be useful if we look at this expression as applied to rotational work. Now, I'm getting a little bit ahead of what we've done in class so far. We've not dealt with rigid bodies and rotation yet, but stick with me nonetheless. So this has units of power, if we're thinking of it in terms of linear forces. The work done look like a force times a displacement. If we consider the special case where the force is constant, then the derivative of the work, right, maybe it's better to break this into two steps, d by dt of f dot dr. If we consider the special case where the force is constant, this would look like f dot dr dt, okay? Which, of course, just has dr dt as velocity, so this just looks like f dot velocity. Okay, so force, if force and velocity happen to be aligned, then we could say that power is equal to force times velocity. Likewise, for rotational systems, we'll deal with this more thoroughly later. For rotational systems, you'll have something that will look like power is equal to the inner product of torque and angular velocity. Okay? So again, let's suppose a special case where these things are aligned. So that might be, let's see if I can do a three-dimensional drawing here. You might have a tire that is powered by an axle, okay? And so here's the tire, here's an axle running up to it, and you might have an associated torque that runs through the axle, and as long as that axle is not bending, torque and omega, the angular velocity, those two vectors, and if you want to think of them as vectors, remember the right-hand rule, right? By the right-hand rule, omega and tau would both point in towards the center of the axle. These two are aligned, so power would be torque times angular velocity. Okay. So the video will demonstrate kind of exactly kind of how that plays out for vehicles. What you'll see in that video is another, like getting to the top of a mountain quickly is a demonstration of power, how being able to spin tires is a demonstration of power. Well, why is that? Of course, because, again, let's draw our tire here. Spinning your tires is a matter of generating a certain amount of force, more force than friction can produce. We talked before about how static friction is an inequality. Okay, we'd have something like force of static friction is less than or equal to mu s times a normal force. So the static force of friction can only be so big, and once the engine somehow generates enough force to overcome that, the tire begins to slip. Now, if we think about this force applied ultimately by the engine, let's call that F sub E, with an associated lever arm here, let's call that lever arm R. So assuming everything is perpendicular, we've got that R times the force of my engine is that torque, and we're trying to compare whether this is greater than the force produced by friction, which is given by mu s times a normal force. Okay. Now this thing also has a lever arm R. Okay, so it turns out that really these things can both be thought of as torques if you want to think about how those forces are seen from the axle. So your ability to spin the tires shows that you have a certain amount of torque, more torque than friction can react. And even that 100 horsepower car can generate enough torque to spin the wheels. You've probably all been behind the wheels of a weak car where right when you're starting to move from a stop, the tires have spun. So if we think about that torque, okay, so looking at this equation above, torque is equal to power divided by omega in the case that this inner product, these things are aligned, and therefore it's a scalar equation. What this means is that in order to have enough torque, okay, so the more that the omega goes up, the more that the power needs to go up too, so that when you do this division, you know, if you're going 10 times as fast in terms of the wheel's angular velocity, you better have 10 times as much power if you want to get to the same amount of torque you had before, in particular the amount of torque it takes to break the wheels free from friction. So being able to generate that torque when omega is higher is a direct demonstration of power. Likewise, being able to generate a large force when something's already moving quickly, in a translational sense, is a direct measure of power. So if you've ever tried to push on a car, you might have noticed that it seems like you can push with less force as the car starts moving faster and faster. That's because humans are power limited. In fact, as engineers, we need to understand that not only are machines and humans limited in terms of the power that they can produce, but that we don't even do it with 100% efficiency. The next definition that we're going to look at is this kind of efficiency. Specifically, we're talking about mechanical efficiency. Okay, so this is denoted as epsilon. Epsilon is equal to the power you get out, power output, divided by power input. And I hope you can all see that this is going to be a quantity that will be less than 1. We're never going to get more power out than we have going in. Just to give you, so let me just make sure to capture that note. Epsilon is less than 1 for any real system. So as some examples, solar cells, they tend to have an efficiency of about 20%. water turbine. You can actually have very good efficiency in the ballpark of 90%. Combustion engine, like in your car, combustion engine, you should expect an efficiency of only about 25%. And interestingly, that's not too far away from the efficiency of human muscle. Human muscle, about 20%. Okay, so that's what we mean by power, and that's what mechanical efficiency is. So now is the best time to quickly look at the attached video that will demonstrate what I was saying about power being demonstrated by generating enough torque to break friction as speed is the angular speed, or if you want the translational speed of the car, is higher.